Section 5.4, Factoring and Solving Polynomial Equations. So we're going to be basically using the same methods to factor polynomials that we did to factor quadratics. And hopefully when you factored quadratics, the first thing you always looked for was a GCF. By factoring out a GCF, first of all, it's going to make the factoring easier. And sometimes when you get to polynomials, by factoring out a GCF, it's going to make the factoring of the polynomial possible. So the first one, if we look at, you will see that they each have a factor of y, so we can factor out that factor of y, and then we're left with y squared minus 4y minus 12. And then we are in fact left with a quadratic, and conveniently this quadratic has a leading coefficient of 1, so it should be as simple as saying what multiplies together to give you negative 12 that adds together to give you negative 4. And you need to make sure that you keep that first GCF that you factored out. That y is part of that first expression, so make sure that you don't just drop that y that you factored out. And then this will factor as negative 6 times 2 gives us negative 12, and negative 6 plus 2 will give us 4. So my factors are y minus 6 and y plus 2. The second example, you'll notice that they each have an x and they each have a factor of 3. So we can actually factor out a 3x. We're going to be left with x squared plus 10x plus 25. And again, we're left with a quadratic. And again, conveniently, this quadratic has a leading coefficient of 1. So what multiplies together to give you 25 that adds together to give you 10? Again, don't forget that factor of 3x that we factored out, but those two factors will be x plus 5 and x plus 5. I'll accept this as an answer. I would also, if you notice, that x plus 5 would be x plus 5 quantity squared. The third example. So both of these terms have a factor of g cubed, and they're both divisible by 5, so we can factor out a 5g cubed. We'll be left with g squared minus 16. Now I'd like to think that you're beginning to recognize when you see a difference of perfect squares and how easily a difference of perfect squares will factor. The square root of g squared is g, and the square root of 16 is 4. So we still have that 5g cubed, and then this will factor as g plus 4 and g minus 4. And I accidentally changed into an x mid-problem. This should be a g plus 4 and a g minus 4. Now when we start to factor our sum and difference of perfect cubes, you need to recognize, first of all, when you have a perfect cube and that you're adding or subtracting them. And these actually do follow a pattern. So the first thing you'll want to do is determine what the cubed root of the first and the second term are. So obviously in this one, the cubed root of a cubed is a. The cubed root of b cubed is b. And perfect cubes, sum and difference of perfect cubes, will always factor as a binomial and a trinomial. And the binomial is always going to be the cubed root of those first two terms. And then we're going to multiply those first two terms together in every way that we can. So a times a will give us a squared, a times b, and then b times b. As for the signs, well, if we have a sum of perfect cubes, then in the first parentheses, we're also going to add. In the second parentheses, that's always going to be the opposite sign, and then that's always going to be a plus. So again, when we have the difference of perfect cubes, the cubed root is a and b. So in the first parentheses, I have a and b, and then I have the a times b, and b times b. Since my original problem was subtraction, my first parentheses is going to be subtraction, and then the opposite of that, which is addition, and then that one's always plus. So now let's put this to use in an actual problem. So 27x cubed plus 125. Well, you'll have to start beginning to recognize what your perfect cubes are, but 27x cubed is a perfect cube, and its cubed root is 3x. The cubed root of 125 is 5. So in my first parentheses, my binomial is going to have a 3x and a 5. And then I'm going to take 3x times 3x, which would give me 9x squared, and then 3x times 5, which would give me 15x, and then 5 times 5, which is 25. Since I'm adding in the original problem, my first parentheses is going to be plus. The opposite of that would be minus, and then that's always plus. And that's as far as you can factor this. When you factor a perfect cubes, the trinomial that you end up with will never factor. If we look at the next one, well, negative 2d to the fifth is not a perfect cube. So you might say, well, this can't factor. But remember, you need to be making sure that you're looking for a GCF. So we could factor out a negative 2d squared. And then we'll be left with d cubed minus, don't forget you factored out a negative, 125. Now as we look for our perfect cubes, the cubed root of d cubed is d. The cubed root of 125 is 5. Again, don't forget that initial GCF that you factored out, but then in our first parentheses, our binomial is going to have the d and the 5, and then we're going to take d times d, 5 times d, and 5 times 5. My original parentheses had a minus. The perfect cube that I'm factoring had a minus, not the very original problem. So in my binomial is going to be minus, the opposite of that, which is plus, and then that one's always plus. And there you have factoring perfect cubes. All right, so now we're going to factor by grouping, and this is not new. We used this method when we factored quadratics. If you recall, when we had a trinomial and we had an a x squared, we would multiply the a times c, and we would ask ourselves what multiplies together to give us a times c that adds together to give us the b. And we would use those two terms to break apart that middle term of our quadratic. So we're going to use that same idea, except we've already got 4 terms now. And so we're going to look at this. First of all, I need you to correct in your notes. This should be a 45t squared. In case yours doesn't have that squared on it, make sure it does. And now we're going to look in the first 2 terms. The GCF that we can factor out of the first 2 terms is going to be 9t squared. We're going to be left with 3t plus 5. Now what can we factor out of negative 3t minus 5 so that we're left with 3t plus 5? And that would be a negative 1. Now if you recall from when we factored our quadratics, this can be rewritten as 3t plus 5, and then we would be left with 9t squared minus 1. Now with quadratics, once you factored them, you knew you were done. But when you're factoring polynomials, you need to keep looking at whatever you're left with and see if you can factor it again. Hopefully you recognize that this second parentheses is the difference of perfect squares. So we still have our 3t plus 5. Then the square root of 9t squared is 3t, and the square root of 1 is 1. So this is going to factor as 3t plus 1 and 3t minus 1. Example number 7. Well, obviously we can see we can factor out a 10. So when we factor out a 10, we're left with x to the 4th minus 1. Well, anytime you have an even exponent, you're going to have a perfect square, because x squared times x squared would give us x to the 4th. If I had x to the 10th, well, x to the 5th times x to the 5th would give us x to the 10th. So x to the 10th would also be a perfect square. So again, hopefully you're recognizing that we have a difference of perfect squares. So we have our 10, and then the square root of x to the 4th is x squared plus 1 and x squared minus 1. A very common mistake that's made is people see this perfect square and they think that they can factor it. You in fact cannot factor a sum of perfect squares. You can only factor a difference of perfect squares. So we can factor the second binomial. We're going to have 10. The x squared plus 1 does not factor, but x squared minus 1 factors as x plus 1 and x minus 1. Example 8. So again, we're going to look for our GCF. Do we have a GCF? Well, everything is divisible by 3, and everything has an m squared, so we can factor out a 3m squared. We're going to be left with m to the 10th plus 18m to the 5th, plus 17. Now, we can factor this in the same manner that we can factor a quadratic if we had an exponent of 2. And the way you can look at this, to help you understand this hopefully, is that we could rewrite m to the 10th as m to the 5th squared. So we have this parentheses squared plus 18 times these parentheses plus 17. And so now we've got our quadratic. So we can think about that m squared, or m to the 5th, as being an x. So we actually have an x squared plus 18x plus 17. And how would that factor? Well, again, the coefficient is 1. Leading coefficient is 1. So what multiplies together to give you 17 that adds together to give you 18? Again, don't forget that GCF of 3m squared. So that would factor as x plus 17 and x plus 1. But in fact, it's not an x. It's actually an m to the 5th. And so there we've factored. Again, you would need to look at these remaining factors and see if you can factor them, but they're not trinomials, they're not difference of perfect squares, and it's not a sum or difference of perfect cubes. So we're in fact done. Now everything we've done so far has just been expressions that we're factoring, but so what would be the difference if we were asked to find the solutions? Well, when we find the solutions, we're given that it's equal to something, so we can find what it's equal to. We can find x. So the first thing you need to do is get it equal to 0. I would recommend keeping that leading coefficient, when it's in standard form, being positive. I just personally think it's easier to factor when it's positive. And now you're going to look for a GCF, and they're all even, so we can factor out a 2, and they all have an x. So when we factor out the 2x, we're left with x to the 4th minus 6x squared plus 8. So again, treating this one kind of the same way we did that last one with the x to the 10th, what multiplies together to give us 8 that adds together to give us negative 6? So we're going to have x squared, because x squared times x squared would give us x to the 4th. And when we get our middle terms, the x squared and the x squared will add together to give us that 6x squared. Those two terms will give us our 6x squared. So we're going to have minus 4 and minus 2. Don't forget, it's still equal to 0. And don't forget to look and see if you can continue to factor it. So x to the 4, or x squared minus 4 is a difference of perfect squares. Factors as x plus 2 and x minus 2. And 2 is not a perfect square, so we're just going to leave that as x squared minus 2. Now, the zero product property says that any one of these factors has to equal 0. So we're going to set them all equal to 0. 2x equals 0 gives us that x equals 2. Setting x plus 2 equal to 0 gives us x equals negative 2. Then we get x equals positive 2. And then we get x squared equals 2. So we have to take the square root. Now don't forget that when you take the square root, it's going to be a positive and a negative answer. So the other thing I want to point out is that we have 1, 2, 3, 4, 5 solutions. We're going to talk about this more in a few days, but the number of solutions is always directly related to the highest exponent, the degree. So the degree of your polynomial is going to tell you how many solutions you should have. If you have any questions, you know what you should do. Come to class and ask them.